Hey, so a summary for you on virtual member functions. A virtual function in a derived class overrides the base class version of the function, and when declaring overriding, or in other words virtual functions in derived classes, it is unnecessary to declare them as virtual, since overrides of virtual functions are also virtual. Okay, so you don't have to actually specify the overriding function in the derived class as virtual, but overriding functions in derived classes can be declared as virtual to make it easier for the reader, in other words the programmer, to follow the class definition in the inheritance hierarchy. The overriding member function signature and return type must match exactly the function of the base class, so the function that you are overriding. If the return type is different, then you'll get an error. We can also redefine the virtual function instead of overriding it. Now to do that, you cannot only change the return type, the signature, or in other words the argument list must differ also. If you change only the return type, you'll get an error. But if you change the return type, maybe also change or add a formal parameter, then basically you are going to redefine that function instead of overriding it, and that will basically be statically bound in that case, as we'll see in upcoming examples. In the previous lesson we talked about the fact that you can qualify redefined functions, and in that way you can specify the specific version of the function that you want to call, maybe from a base class. You can do the same thing with overridden functions. You can qualify overridden functions, that is to call the specific override required or the specific override that you need. So for an example, with a pointer to a derived object on the heap, you do the arrow operator and then you qualify the function name. So we do base class, the scope resolution operator, and then the overridden function, or in other words that function in the base class, and then it will invoke that specific version of the function. Just a couple of examples again. In Visual Studio, I have the base class. In the public section, I have this toString function. It prints out base toString. And then I have the derived class, which publicly derives from base. In the public section, I override the toString function. I have virtual void toString. Of course, this is also virtual in the base class. And you can see the signature and return types match for the toString function as defined in the derived class and also for the base class. And of course in the derived class I'm simply going to print out derived toString. Then in the main function I have a pointer to base called base pointer, but I allocate an object of type derived on the heap, and then I do base pointer toString, and then later on I'll go and delete the base pointer again. Let's just build and run to see what we get. We should get the derived version. As you can see, that's what we get. We get derived toString. Now what happens if we make some changes to this? Firstly, let's go and remove the virtual keyword in the derived class definition of toString. Build and run that. And you can see we still get derived toString. So if the function is declared virtual in the base class, then it's also going to be virtual in the derived classes, or in other words, the overrides of that function is also going to be virtual. Now as I mentioned, we simply specify these as virtual in the derived classes as well, just to make it easier for the programmer to understand what's going on. And in that case, you don't necessarily have to look at the base class definition, because as we've seen, we can separate out our classes into different files. So let's go and change the return type now to int. This is still virtual. You will see we get an error. Return type is not identical to nor covariant with the return type void of overridden virtual function base toString. But we can go and change the signature. We can add a parameter. You can also, in some instances, get away with removing const. Let's say in the overridden function, for some reason you want to make changes to the state of that object. Go and build and run this, and we'll see what happens. So of course we'll get an error because we actually have to return something from this function. I'll just return some integer value such as 0. Build and run again. And you'll notice that we get base toString now. Remember, the object on the heap is an object of type derived. The pointer is a pointer to type of base. So that means we do not get this version of the function. So it's similar to a static redefinition as opposed to an override in this case. And the same thing if you change the parameter list. So I'll make sure this is const again, and I'll change the formal parameter list so we have an int x here. And I'll actually just return 0, or maybe we can return x. If you build and run, we will once again get the toString function as defined in the base class. To actually call the version in the derived class, what we can do is I'll do a pointer to derived called derived pointer, and I'll also allocate a new object of type derived on the heap. Then I'll do derived pointer toString and I'll pass in 5. Maybe I'll do that in a console output statement, so cout derived pointer toString end line. And for right now, I'll just comment this right here out. Comment that out as well. Just make sure to deallocate whatever derived point is pointing at. Build and run that. And we get derived toString printed out. So it calls the toString function as defined in derived. And then it prints out 5 in the console output statement, which is right here. Okay, because that's going to return what we pass in. Now I'll just go back and I'll make sure that these return types and signatures match. Okay, to take advantage of polymorphism. And I'll remove this right here. That as well. So those two function prototypes match now. And then in main, I'm just gonna do something like that. If I build run now, we should get derived toString. Now let's say we want to explicitly specify which override of the toString function gets invoked. Well, that's similar to what we discussed in the inheritance lesson. We can simply qualify the function name. And remember, use the class name, so in this case base, the scope resolution operator, and the function name. So even though this derived pointer is now pointing to an object of type derived on the heap, and even though we are making use of polymorphism, so we have virtual functions, we can still go and explicitly specify which version of the function to invoke. Build and run, and as you would expect, we get base toString now. Here's a different example for you. I have a parent class, and I also have the toString function in the public section, but in this case it's going to print out parent toString. Then I have a child class, which publicly derived from parent. I override the toString function, and this is going to print out child toString. Then I also have a grandchild, which publicly derived from child, and I override the toString function once more, and this is going to print out grandchild toString. Then in main I have a pointer called grandchild pointer, which is a pointer to type of grandchild, and I assign an object of type grandchild on the heap. Then I do the grandchild pointer toString in this statement, and then in the next statement I qualify the toString function from the child class. So in other words, in this statement I want to invoke the child version or override of that function. Then in the next statement I also explicitly specify which override I want to invoke. In this case, the parent override or version of the function. So I do parent, scope resolution, and toString again. And of course I want to go and deallocate that again later on. Build and run. You can see we get the toString as defined in grandchild, the toString as defined in child, and then finally the toString as defined in parent. Okay, we have child and parent. This next section is just a bonus section on the virtual table and the virtual table pointers. You don't have to worry about this section too much because it is taken care of behind the scenes, so we don't really work with this directly, so we don't work with the virtual table and the virtual table pointers directly. I'll just be demonstrating on a high level how polymorphism and these virtual functions work. Okay, an array of pointers to all of the virtual functions of a class is referred to as its virtual table. Now, if an object is an instance of a class that contains virtual functions, the object will contain a virtual table pointer that will point to the class virtual table. So just to reiterate, the virtual table is associated with a specific class, whereas the virtual table pointer will be associated with or contained within an instance or an object of a class. You can think that if an object is an instance of a class that contains virtual functions, then more memory is required to store the virtual table pointer, that is per instance of that class. This can eventually add up if you have many instances of that object. Now, of course, a pointer doesn't take up that much memory as compared to doubles and some of your other types, but still that instance will require more memory as compared to an instance that does not have or that does not contain virtual functions. Also, additional computation is required with virtual functions because basically what happens is the dereferencing of the virtual table pointer to get to the virtual table, and then also dereferencing of the function pointer to add the correct index to invoke the appropriate function. So again, some additional computation with virtual functions that you will not have with classes that do not contain virtual functions. Here's a quick example for you on the virtual table and the virtual table pointer. Now let's say we have some object on the heap. To the left I have an illustration of the heap, and on the heap we have some object. Now of course on the stack you'll have some pointer that points to this object on the heap. That is not in this illustration for space constraints. Now the object actually does not have to be on the heap. It will still contain that virtual table pointer, as we'll see in a later example. But the benefits of polymorphism really comes in when you have objects on the heap, or when you use references of objects as we have seen before. So for that reason, in this example, we are going to use this object on the heap. This object on the heap can contain various members, some member variables, and member functions. And when instantiated, if the class that defines this object has virtual functions, then this instance of the class will have a virtual table pointer. And as you can see, that virtual table pointer is going to point to the class virtual table. Again, this virtual table is associated with the class, and it is an array of pointers to virtual functions. Just for demonstration purposes, again, all of the stuff happens behind the scenes. But let's say that array is called virtual table, and you have index 0, index 1, and so on. At index 0, you can have a pointer to one of the virtual functions, maybe the destructor. We'll talk about destructors in more detail in upcoming sections. At index 1 for the virtual table, that can contain a pointer to maybe some toString function, and at index 2 that can contain a pointer to some set member function, and so on. Okay, now let's say we have this base and derived class. Derived, again, publicly derived from the base class, and in the base class we have a virtual destructor. Now as I mentioned, we'll talk about the destructors in more detail in the next video, but you can also have virtual destructors. Then it also has a virtual void toString function that can print something out, and then also maybe some virtual void setMember function that will maybe set some member to some value. Now in the derived class it has its own virtual destructor, so we do virtual derived here. Destructors are not inherited. And also remember that when a derived object is destroyed, the local destructor is called, followed by its base class destructor. In the derived class we also have a toString function, virtual void toString, that maybe prints something else out. So the toString function is overridden. One thing that I'd like to note before we move on to the illustrations based on this example is that the derived class does not override the setMember function. We do not have an overridden version of setMember in the derived class. So what's going to happen with that? How is that going to work? Let's look at the illustration. In this example we have an instance of the base class on the heap, and so the virtual table pointer is going to point to the base virtual table, the virtual table that is associated with the base class, and the pointers in that virtual table is going to point to the virtual destructor, the virtual toString, and the virtual setMember function that is basically associated or defined with that base class definition. Now in this example we have an object of type derived on the heap. Its virtual table pointer will point to a derived virtual table, so a virtual table that is associated with the derived class. Once more, the pointers in the virtual table will point to the appropriate functions as defined in the derived class. You have the virtual functions to the right again. So of course we have the virtual destructor, the derived destructor in this case. If you destroy a derived object, you want to invoke that derived object's destructor. That destructor will then automatically invoke the base class destructor. Okay, so this is very important. We have to make sure to invoke the correct destructor depending on the object that we have on the heap. As you can see, we also have the toString function that is overridden in the derived class. Now if you remember, the derived class did not override the setMember function. SetMember is also defined as virtual in the base class, and because it's not overridden, the entries in the virtual table associated with the derived class will point to the base or the parent class implementation or override of that virtual function. So in this case, even though we have a derived object on the heap, we do have a pointer in the virtual table that will point to a setMember function. Hopefully you can see through these high-level examples how the appropriate functions are invoked based on the object that you have on the heap, or based on the object that you are referencing if it's a reference instead of a pointer. Again, this is based on the type of the instance or the object, thanks to dynamic binding as opposed to static binding. In this example I have class entity. In the public section I have this toString function again, and then I have private with some members, so I have a double D and a float F. We're not actually going to use these members, they are just for demonstration purposes. In main I do console output size of entity and endline, and if I build and run that, we get something like 16. Now of course you can instantiate it and then pass in the name of the object, and then build and run if you want, and get it in that way as well. To make this more clear, maybe what you can do is, I'll call this class virtual entity, and Then I have a class non-virtual entity. And for the virtual entity, let's go and create a virtual function. So I have virtual void toString. Whereas for the non-virtual entity, you can see we do not have any virtual member functions. Also do it in this way to save some time, so I'm not going to instantiate those classes. We print out size of non-virtual entity and size of virtual entity. If I build and run this, we get 16 as before for the non-virtual one and 24 for the class with the virtual function. You can see the definitions are the same of these two classes. The names differ, they both have a toString function. Non-virtual does not inherit from virtual or anything like that. They have the same members, double D and float F, alright? So the difference in size for the instance comes in because of the virtual functions. Now you can also check this for objects on the heap, so I have a new virtual entity. I allocate a virtual entity object on the heap, and I assign that to an entity pointer, which is a pointer to a virtual entity. And then I have a reference to a virtual entity called entity ref, and I assign whatever entity pointer is pointing at to that entity reference. And then I simply do console output size of entity ref, because this entity reference is basically going to be that virtual entity on the heap now. I'll build and run, and we should still get 24. So that is the one with the virtual function. And I'll change all of those instances to the non-virtual entity and build and run again. And we get 16 bytes in this case. So you can see the non-virtual entity uses less memory than the entity, which is of type virtual entity, which again has virtual functions. Alright, so just a quick demonstration for you. I hope you found this interesting. In this next example, in the base class, we have virtual void toString that is going to print out the member. Then we have virtual void setMember, which is going to set the member. The member is just an integer in the private section. Then derived again, publicly derives from the base class. In the public section, we only have the toString function, and you can see the toString function differs from the one in the base class. So this is just going to print out the string. Okay, in main I construct derived. Then I do derived setMember, and I pass in 5 for the argument. Now remember, the point of this demonstration is that the derived class does not have the setMember function. It is inherited, and just like with non-virtual functions, you can use virtual functions in derived classes. Alright, you do not have to go and overload those virtual functions just to be able to use them in derived classes. The derived class will simply use the base class's implementation. Back in main I do derived dot, and I qualify the toString function to the base version. In the base version, I'm going to do console output member. I'm going to print out the value of the member. So we should get 5 printed out here. Build and run that, and we get 5. And we'll end on the summary on function invocation through pointers and references. As we've seen, calls to non-virtual functions are resolved based on the type of the pointer or reference, whereas calls to virtual functions are resolved based on the type of the object, and that is really where the usefulness of polymorphism comes in and the virtual keyword. That is going to wrap up this video. I hope it was useful to you, and I'll see you next time.